Well, welcome to our video on collapsed core design with BGP, OSPF, and HSRP. In this tutorial, we're going to show you how to set up BGP peering to two different ISPs along with HSRP and OSPF. So let's get started. We have ISP1 here, ISP2. We, the company, are TMNT company with our public ASN 12345. This PI space here is our provider independent IP space, which we received from Aaron. It's a /23. And what we're going to do first is configure the ISP routers for BGP peering to switch 1 and switch 2 here. They're layer 3 switches, and they run an iOS that can support BGP. So let's open up a console session to ISP1, which we already have here, and let's go with ISP2. Let's first configure the Ethernet 00 link. We'll unshut it, and we'll configure it with an IP as stated in the diagram, 76.23.1. We're going to make ISP1.1, and it's 252 mask/30. The ASN for ISP1 is simply going to be 1. Let's configure the neighbor statements to appear with switch 1 on our side. So we're going to be .2, remote AS 12345. And in this case, we're just going to be originating a default route. So let's go ahead and configure that. Okay, let's go to ISP2. Ethernet 00, unshut it, IP address 25.24.1. This is also going to be .1. The ASN for ISP2 is going to be 2. Let's configure the neighbor statements. And we're also going to be originating a default route. Okay, so that takes care of the ISP routers. Let's go to switch 1. And you can see here it's also Ethernet 00, which connects to ISP1. So let's unshut that. We'll configure the IP. Because this is a layer 3 switch, we do have to run the command no switch port in order to turn it into a routed port. So that's why I just configured that 76.23.1.2.255. Okay. Here we see that that Ethernet 00 is connected and up. We should be able to ping the ISP router side, and we can. Let's go ahead and configure the BGP process for ASN 12345, and we'll configure the neighbor statements. Mode AS1, and let's go to switch 2. Same thing for port Ethernet 00. No switch port, IP address 25.24.1.2, and we'll configure the BGP process. As you can see on switch 1, we are receiving the default now via ISP1. It'll just take a minute for ISP2 to come up and to receive the default route from them. So we'll give that a minute. We'll come back to it. Now, what we have here in this collapsed core design, we also have to run an IGP between switch 1 and switch 2. And between them, we'll also be running iBGP. So let's say ISP1 fails for whatever reason. It could be a fiber cut, it could be the a faulty port or whatever, it doesn't matter. Traffic going out through switch 1 trying to reach an external destination will transit via switch 2 out to ISP 2 in this in this case. So let's go ahead and get that set up. We're on switch 1 right now, and we'll just go into Ethernet 01. We'll unshut it, and we'll configure an IP address. 1.1. We'll make switch 1.1. No switch port. Let's try that again. There we go. And we'll go to switch 2. Oops. We'll make this .2. Okay, and now we're just going to enable OSPF on these links. So to do that, you could either do it under router OSPF, or we could just do it right here under the interface, IP OSPF 1 area 0. But what we're also going to do for iBGP, best practice is to peer with the loopback addresses when you're running iBGP, because a loopback does not go down. If you have an interface and you want to run iBGP on it, if that interface goes down, the BGP session will also drop, and we don't want that to happen. So we're going to configure 2 loopback addresses, one on switch 1, one on switch 2. For interface loopback 0 on switch 1, the IP address is going to be, let's keep it simple, we'll make it 1.1.1.1. And on switch 2, 2.2.2.2. Now in the real world, what you'll probably do is configure the loopback addresses with an IP in your PI space here. But in this case, I'm just trying to keep things going along quickly, so I'm configuring an easy IP address just to show you how things are done, which is why I'm using 1.1.1.1 and 2.2.2.2. So now that we have that done, let's go back into the BGP process here, and we'll start to configure iBGP between switch 1 and switch 2. So these are the commands that you will need. You need to specify the ASN. The update source is going to be the loopback 0, and you want to specify next hop self. So you want to use the next hop self command because when you advertise something within iBGP, it does not change the next hop. So in order to modify the next hop, in this case for the next hop to be 2.2.2.2 of the routes learned via switch 2, you want to specify next hop self. And I'll show you an example of what the next hop will look like in the routing table once everything is configured. Let's go ahead on switch 2 and we'll configure the neighbor statement for switch 1 as well. So we just need to give it a few seconds. It'll come up eventually. Oh, you know what I forgot to do? We have to go back into the loopback interface, and we have to advertise the loopbacks into OSPF. I forgot to do that. And we'll do the same thing. Now we have a reachability between them. Great. So this BGP session should be coming up. There we go. And as you can see, in the BGP table we have the two default routes, one being learned from ISP2 and the other now being learned from switch 1, which gets its default from ISP1. And vice versa, same thing we should see on this side. And we do. We see the two defaults, this one learned iBGP, and that's that. So now what we're going to do is we're going to configure HSRP for a couple of the VLANs in this diagram. So we have here VLANs 10, 20, and 30. Typically what we've seen is when you run a collapsed core design, you really have two options. You can configure layer 3 between these core switches here, and then you have trunk links going down to these access switches here. These could all be trunk links, or if you don't want to run HSRP, what you could do is you have a routed access layer, it's called, and you would configure OSPF between the core switches and the access switches, which means that the default gateway would now reside on the access switches. But for this example, what we're going to do, we're going to stick to layer 2 trunking between the core switches and the access layer switches. So let's go ahead and get that set up. We'll start with switch 1 and switch 3. So here we have, let's create the VLANs on switch 1. Well, first what we could do is show BTP status. We'll check what mode we're running in. And this is operating in server mode. Best practice in the real world, you really don't want to use server client mode, you want to use transparent. So we're going to set that here so we can show you how that works. And let me go ahead and do that on switch 2 as well. Now this means that you have to create the VLANs on each of the core switches, but it's a lot safer, and you won't have any undesirable effects due to human error or whatnot. So let's go back to switch 1 and we'll configure Ethernet 1.0. We'll unshut it, and what we're going to do, switch port trunk encapsulation .1Q, switch port mode. Now here you can set different types of modes. I'm just going to stick to switch port mode trunk. And if you want to do trunk security, you could specify what VLANs are allowed. In this case, we would use the native VLAN and VLAN 10. This is just assuming that only the VLAN 10 is going to live on switch 3. If you want to add additional VLANs to switch 3 that will be allowed to access it, you would have to modify this switch port trunk allowed VLAN statement to include those VLANs. But for now, we'll stick with 1 and 10. Okay. Let's go to switch 3. And this is going to be port 00. No shut. Now the encapsulation has to match. .1Q, switch port mode trunk. Now trunk security is already allowed. It's already specified on the core. I've seen some situations where people just allow all of the VLANs on the uplink ports, in this case 00 and 01 here. But it's always good practice to specify what VLANs are allowed to traverse the uplink port. So we'll do that in this case as well. And while we're here, we might as well do the same thing for 01, which goes to switch 2. setting these access switches to transparent as well. So, show VLAN brief, you can see the VLAN 10 is not created yet. So let's go ahead and create it. We'll give it a name, let's say VPC 6. Okay, so now let's go to switch 2. And we'll create the VLAN 10, name VPC 6. And let's go into the uplink port that's going to switch 3, which is 10. No shut, switch port, trunk encapsulation, .1Q, switch port, mode trunk, switch port allowed, VLAN 110, trunk allowed, it's always good to verify your work after you're done to make sure that you set exactly what you want to set. Let me just check this real quick. And is it the same? Yes, it's the same. Let's go to switch 3. Let's just create the VLAN here as well. Okay. Now obviously in this case, spanning tree is going to be blocking either this link here or this link going to switch 2. Let's see. Once we create the SVI for VLAN 10, we could determine which is going to be blocking. So let's go to switch 1 and interface VLAN 10. We'll create it here. And for VLAN 10, we'll use IP address 100.1. Let's make it .1.17. We'll make this a /29, which is typically what you would do. Let's say if you're a hosting provider and you have a customer who just bought a server from you, you would allocate them a /29, which would be useful in this case for HSRP, because you need a minimum of 3 IP addresses in order to get HSRP working properly. So right now we have switch 1, we'll make this .17. Let's go on to switch 2. Interface VLAN 10, we'll unshut it just in case. IP address 101. Let's make this 18. Same /29 net mask. Now we're going to configure HSRP with the standby command. So here you can specify standby. Here we go. We'll make 1 with the group number, and here's where you specify the virtual gateway. So this is, in this case, it's going to be 100.1.1. and the virtual gateway IP 19. Now this has to be the same on both switch 1 and switch 2. Here you could set various options, different timers, which you should tune if you want to get the best performance out of it. You should always set preemption based on how long it takes the device to boot up. This is in seconds right here, so that's 5 minutes. Here we do the same thing. Okay, there we go. Now we have HSRP up and running. Let's take a look at the VLAN interface. Alright, so now let's go to switch 1 and let's just check spanning tree for VLAN 10. Here we're running the legacy spanning tree protocol. It's not going to be fast, it's going to be slow. In real life, you want to set this on a Cisco device, either to a rapid per VLAN spanning tree or multiple spanning tree. But I'm not going to show you how to do that right now. As you can see here, for VLAN 10, switch 1 is the root bridge, so all of its ports are going to be forwarded. If you look here on switch 2 for VLAN 10, you could see all of them. You could see that Ethernet 1.0 is the root port, and that's happening because we did not configure this inner switch link here as a trunk link. What we would really want to do is convert Ethernet 01, let me see. Okay, so right now it's a router port. What we want to do is convert this back into a switch port with a trunk link and run OSPF over VLAN on that trunk port. So let's do that so I could show you how that's done. And basically what we're going to be creating is a looped design, and that's fine. The spanning tree will block on which on the relevant ports that it needs to, but we really want to have this in this case because if you're a hosting provider or in a data center and you want to be able to use a VLAN on different access switches, you should have a layer 2 link in between your core switches. So let's go ahead and remove this config. We'll save this IP address because we're going to use it again. This right here. So no IP address. Okay, so for this link in between, for the OSPF link, what we're going to do is we're going to use the VLAN 100. And we're going to do this, configure OSPF and the IP on VLAN 100, and we're going to do the same thing on this side. Now, right now I have Ethernet 01 not configured as a trunk, so let's go ahead and configure this as a trunk as well. And we'll just have it pass all of the VLANs in between. And we should see the OSPF adjacency come up very soon. Okay, so now we're able to ping across VLAN 100 over this trunk port, and the OSPF adjacency is forming. That'll take a few seconds, so I'm just going to pause this and resume it as soon as it's finished. Okay, so now the adjacency is full. Let's take a look at spanning tree for VLAN 10 again. And now this is what I wanted to see. Now we can see that the root port is pointing out Ethernet 01, which is going to switch 1. Alright, that's a lot better. So now we have HSRP configured, we have OSPF configured, we have a BGP configured, and we have this layer 2 trunk link with OSPF formed over it. Alright, so now let's go back to switch 3, and we can see that this computer here, this PC, VPC6, is connected to port Ethernet 1.1. So what we're going to do, let's just double check the VLAN database, make sure VLAN 10 it's there. So we'll go Ethernet 1.1, we'll unshut the port. If you want, you can set a description, VPC6. And what we're going to do is simply make this an access port for VLAN 10. Now when we configure an IP on VPC6, we should be able to ping the virtual gateway configured between switch 1 and switch 2 with HSRP. And we're going to test by shutting down one of these uplink ports. We still should have reachability to the virtual gateway and beyond. But first, another best practice, You could either do this at the global level on the switch or on the port level, is to configure port fast. And as you can see, it throws up a warning. Port fast brings the port up automatically. It does not send any TCNs out. It's basically a mechanism to keep your layer 2 topology stable and from generating excessive noise. So now that we have all this configured, let's go to VPC6 and we'll configure an IP address on it. Let me just go back to switch 1 and double check what IP range I had configured for VLAN 10. Alright, so the usable range right now is going to be 100.1.1.20 to .22. So you're going to have 3 usable addresses here in this range, where we're going to configure .20 on VPC6. Okay, so VPC6, we're going to use the IP command 100.1.1.20/29, and the gateway is .19. That's the virtual gateway. So that virtual gateway is going to be up, regardless if switch 1 goes down or if switch 2 goes down. Let's see if we could ping. Alright, there seems to be a slight issue. Let's take a look. We have switch 1 and switch 2. Oops. Okay, so both of these groups for HSRP are saying that they're active, which shouldn't be. One should be active and one should be standby. And look at this, standby router is unknown. So it looks like the HSRP UDP packets are not getting across that inner switch link that we have. And what you should see here, the active router, in this case switch 2 has a lower configured priority, which I set for when I was testing right now. This should be the standby router, and switch 1 would be the active router. But that's not the case right now. I'm not sure if it's an issue with the software I'm using on my server. But what would happen is on VPC6 you would be able to ping .17, which is switch 1, you'd be able to ping .18, which is switch 2, and you would also be able to ping .19, which is the virtual gateway. So I'm going to leave this lab here with that. If you want to test on your own server with UNetLab, you can set up this same topology here. If you have any questions, feel free to give us a shout via email, and hope to see you soon with the next video.